Jared. I'm from Lacework Labs, the security research team at Lacework. Today, we'll be talking about the Strace utility and how it can be useful in troubleshooting Unix applications in your day-to-day activities. Whether you're a systems administrator, SOC analyst, developer, or somewhere in between, Strace probably has some functionality that can be useful for you in your day-to-day job. Let's go ahead and get started with understanding how we can leverage Strace for a variety of tasks. So first off, what is Strace? Well, per the Linux man pages, Strace is a diagnostic, instructional, and debugging tool to solve problems with programs for which the source code is not readily available. If you've ever been in a scenario where an installed application just keeps crashing and the internet doesn't seem to have the answers this time around, or the developers are saying it worked on my machine, I'm not sure why it's not working on yours, Strace can come to the rescue here. Additionally, if you find yourself in the predicament of a binary that shouldn't be there and you want to know what it's doing, Strace can also provide some information in that front as well. Strace does this by displaying all system calls the binary is making. So at this point you may be thinking to yourself, okay, but what's a system call? A system call is a standard way for user-land processes in Linux to communicate to the kernel. So when you think of reads, writes, connections, etc., all of those function calls that you might see in a C program, those are actually system calls occurring underneath the hood. So by displaying all this information to the end user, you can then start to understand, okay, I don't have the source code of this application, but I kind of have an idea right now of what's going on based on the function calls being made. With all that being said, the best way to learn is to dive right in. So let's go ahead and start with our first example of a misbehaving application that doesn't really have great error handling, so we don't know why it's crashing. Let's see how Strace can help us in this example. Alright, so let's go ahead and get started and run a couple example programs to get an idea of what Strace can do for us. So first, I'll start off by just running the program, and it's going to be in bins, example 1. So immediately we just see error get printed to the screen. Now, I'd venture to guess that at some point in your career of just being involved with computers in general, you've gotten a nondescript error message and then become increasingly frustrated when there's lack of documentation, or online everyone's just getting the same thing, and where do you go from here? So for this specific example, let's go ahead and just do a gentle introduction to Strace, where we'll run Strace and then also the binary that we just did before. So that's just strace and then bins example1.bin as the file argument. Whoa. Immediately we see a bunch of data get printed to the screen, and this is going to be a little bit harder to parse than we thought. So let's go ahead and hit up and rerun that same command, but this time we're going to redirect it to a file to make it a little bit easier to walk through. So to do this, we're going to do -o, and I'm just going to call it example1.log. All of the little flags and kind of tips and tricks along the way, those are going to be in the README of the GitHub. So don't worry about trying to write all these down. There's going to be a nice little cheat sheet that you can take and carry along with you for the exercises, but then also for practical examples that you'll find yourself using Strace. So I'm going to go ahead and then just rerun this command, and then we again see error get printed to the screen. But this time we have a nice little log file that we can expect. So I'm going to go ahead and open this up with Vim. You can go ahead and choose the editor of your choice. I'm just more familiar with Vim. And we see right at the top of the file the exec call being made to our bins example1.bin, and that's fantastic. However, we are more focused with the error that's going on here, and to get to there, we can go ahead and just jump to the bottom of this file. So I'm just going to do a Shift-G in Vim to go right to the bottom. And then, sure enough, we see that error on line 35 getting written to the screen with the right command. So at this point, we go, okay, we see the error getting written to the screen. Let's go ahead and go up a couple commands and see if we can find the origin of why the error is getting printed to the screen. And sure enough, up at line 31, at an open@ call, we see /temp, this file should not exist. And then over to the right, you see -1, no such file or directory. So in this toy example, that's just trying to get people more exposed to Strace, we see that temp, this file should not exist, actually should exist in order for this program to execute appropriately. So let's go ahead and copy this, and we will create that file and then see if we can re-execute. So I'm just going to go ahead and execute on the touch command to create that file, and then I'm going to go ahead and just rerun this command. And sure enough, the file exists, everything's right with the world, and we get that printed to the screen. Fantastic. However, I want to go back to that log file and show some practical examples of other things you can do along the way here, because there's unlikely a chance that things are going to be this straightforward in the real world when you're troubleshooting, live applications, whether it be in production, or you come across something that is just, making you scratch your head and you're like, I have no idea what this is. So I'm going to open up that log file again. And let's go ahead and jump back to that line 31 where we see that open at call. So by no means am I a syscall master. I have no idea what these parameters are supposed to be in what order, and you're going to run across a bunch of syscalls that you may or may not be familiar with, but you get used to them over time and you start picking up some things. However, a nice thing about just kind of leveraging Vim here to stop you from popping on over to Google and typing it in, which by all means do, but the nice thing with Vim, you can do a quick Shift K, and that will immediately take you to the man page of the underlying syscall. So as far as a workflow goes, when you're getting your groove and you're going through a bunch of syscalls and trying to figure out what the parameters are for these functions, you can go ahead and just do a nice Shift K and then get dropped into the man page. Go up and down, say okay, got it. Go ahead and do Q and get right back to the log file at hand here. Just a handy little trick I wanted to pass along for your workflow, whether that be real world or CTF stuff. So with that being said, there's a couple other really neat things that this little example lets us do with Strace, and I want to open up the source code right now before we go into those next steps. So with our example file here, we see that we try to open the file at line 9 and with read-only flags. And then if the file descriptor returns a -1, we'll go ahead and print an error. Otherwise, we will print file exists unless that file descriptor is 99. If that file descriptor ends up being 99, we get a neat little thing printed to us of, whoa, we should never have gotten here. So the example that we're kind of showing here is mostly CTF focused, but also there's plenty of examples where we need the return value of a function to be a specific value in order to go down a code path that we want to see. So if we go ahead and look at open, we see that open, the function, returns an integer. So let's go ahead and see if we can find out what type of integer this is. So the return value of open is a file descriptor. So you're going to get an integer returned to you. Typically, this starts at, I believe, 3 and then goes on from there depending on how many files are opened. I could be incorrect on that, so please don't quote me. However, seeing in our contrived example here that we need a file descriptor to be 99, well, that's just not going to be possible based on the return values. So what we can do is by leveraging Strace, we can actually go ahead and inject ourselves into the execution process and then go ahead and rewrite the return value to be 99. And to do that, we're going to leverage the inject option of Strace, and I'm going to go ahead and walk you through what that looks like for this kind of example here. So going back to the log here of what the normal Strace flow looks like, we have this lovely open at call, and it's returning -1, which is why we're getting that error. And I will go ahead and actually split this so we can look at the code as we go ahead and look at the Strace log as well. So we see we get a -1, and that's going to go ahead and take us to the print error. If we get a 99, we should get, whoa, never should be here. Otherwise, everything's right with the world. So we want to get 99. Strace allows you to say, hey, at this syscall, I want you to go ahead and overwrite the return value. But you need to know where in the syscall hierarchy your call is being made. So is it the first one? Is it the second one? Is it the third one? And how often do you want it to be called? So in this case, if I go ahead and count the openats, we have 1, 2, 3. So we have 3 openat syscalls, and I want to go ahead and influence the third one with the strace the strace inject command to go ahead and overwrite that return value. So with the idea here being the openat syscall, the return value needs to be 99 when it is the third time that we see openat get called. With all of those being our parameters, we can go ahead and create something that allows us to do just that. So I'm going to go ahead and we're going to do another log file so we can kind of see us injecting and overwriting the file, or overwriting that return value. And then our next command here is going to be this -e for inject equals openat. So that is the syscall that we want to pay attention to. We want to go ahead and make that return value 99 when it is the third time that you've seen it. This is very configurable for whatever particular parameters that you need to execute on. So maybe it's every time you see a certain syscall, always make the return values 0 or -1 or what have you. And it's also a really unique way to start poking at applications and making them go down code paths that they may not normally go down. For CTFs, this can be like a really nice way to take out some of the lower hanging fruit challenges without even having to spend too much time in a debugger or disassembler. Specifically for scenarios where you have to take one code branch to be successful and the other one which would not print the flag. Regardless, let me just go ahead and run this and then jump into the logs and show you what this looks like. So, haha, success. We should never get there. So immediately, feeling good, looks like our inject worked. Let's go ahead and take a look at what this actually looks like. And again, going to go ahead and jump down here. And we can see at our line 31 on our new file at openat, we are overwriting this return value to be 99. And we can see, we've injected, success. And then we get this printed, whoa, you should never get here. So again, while this is a contrived example, I hope you can see how powerful this can be when you start overwriting return values to make code take different paths that you didn't normally want it to. Or even for just like CTF challenges, this is a super handy thing to keep in your back pocket. So going back to that syntax, well, what if you wanted to do it every time? Well, you could just do 1+. So every time you see it, and then every time after that, go ahead and overwrite the openat syscall and make that return value be 99 no matter what. But when we do this, we get a crazy error of, whoa, we couldn't do this loading shared library thing. And that's because we're calling openat a bunch of different times before the program even gets loaded and executed. So this is something that, while this is a contrived example, you need to spend a little bit of time with the program to understand where exactly the syscalls are getting made, if you should only make that syscall once, or if you start going down crazy code paths where you got to make the changes multiple times. It's just something to be aware of. It is a super powerful tool, and I hope that you enjoy the exercise in the GitHub repo that comes along with this for everyone to play around with and get a little bit more comfortable. Alright, so now that we've gone ahead and given an example to get ourselves a little bit more familiar with strace, so if you have a single process doing some stuff and we can poke and prod and get it to go down different code paths, that's great for one single process. But what about the scenario where you have a process that's fork and execing and causing a bunch of child processes to spawn? Well, when that happens, you actually have to add a couple more command line flags so that strace knows to follow those child processes to inspect what they're doing. Otherwise, there's going to be a bunch of data that you're not aware of, and the really interesting parts you may be missing. So with that being said, I want to keep this as hands-on as possible, so let's just jump right into the next example. Okay. So this time we're going to go ahead and take a look at how we can handle any kind of application that is forking and spawning child processes and how to stay organized a little bit. So typically with Linux applications, if specifically speaking in a malware context, if there's like an initial dropper that may survey the system or just write its secondary payload to disk and then fork exec the payload, say it's a cryptocurrency miner or something else. What ends up happening there is you have a child process created from the parent process, and being able to create unique files for all of these independent processes will make our analysis lives much easier later on when we're gathering all the data and doing a timeline of events. So with that in mind, I'm going to go ahead and show you some command line flags to use with Strace. So when you're doing kind of the malware analysis thing, or even just troubleshooting an application that's just spawning a bunch of child processes and you kind of track them down, how to do that a little bit easier. So before we jump into that, I'm going to go ahead and show you what the little program that we're using today looks like, so that way there's a little bit more context to the kind of actions that we're seeing with the parent-child relationships. So I'm going to go ahead and open up example 2. And if we look here, we have a password of secret123, and we're going to go ahead and loop through and fork several times. And then each time we fork, we go ahead and we copy that password over, we do a little bit of malloc, we end up creating a log file, and we write a little bit of data to that log file. Nothing super crazy, but this ends up creating a bunch of child processes, which is pretty good for the little contrived example that we're working with here. So with that being said, I'm going to go ahead and show you what it looks like when you don't apply the appropriate command line arguments to be able to trace child processes. So I'm just going to go ahead and run strace. We'll run example 2, and I'm going to write this out to example2.log. And we'll go ahead and take a look. There's no standard out this time. So just like before at the top, we see our nice exec followed by the path to our binary. And then as we go through, we will see a bunch of get pids, several opens, fstats, writes, close, clone, etc. So the interesting thing here though, as we look, and we saw that there should have been a bunch of different files getting created, we only see this one right here. So let's go ahead and take a look in the temp directory and see if this is the only file that's there or if there's several. So looking over in temp and just kind of grepping for log, we see, sure enough, all around the same time, we had a bunch of files get created, some with a little bit more data than others. So clearly, our strace output is not kind of showing us the full picture. And just to kind of demonstrate this, I'm just going to grab this log file at random, and let's go ahead and open that file back up, and I'm going to search for this pattern, and sure enough, it is not found. That's because this file was created in one of the child processes that is not caught in this output. So let's go ahead and demonstrate kind of the same concept another way, just to see how much data are we missing. So I'm going to go back and execute this same command of just strace with the argument to our second binary example. However, this time I'm going to do a -c, and this is going to go ahead and give us statistics about all of the syscalls that are happening with this given binary. So in this nice little format, we see the syscall, errors if they occurred, how many times that given function was called, and how long it took to call the functions. So with all this being said, at the total here at the bottom, we can see we had a total of 75 calls. However, as we discussed earlier, we know that there is several forks occurring that we're just not capturing in this data. So in order to capture said forks, we have to go ahead and include a -f here. And this is going to go forth and follow all of the children processes. So let's go ahead and rerun this. And sure enough, we went ahead and attached to all of those processes and now have a much better idea of all of the calls that are occurring in these programs because of all the forking that's occurring. So we went from roughly 70 to over 1,400. That's great, but we still, this doesn't give us the actual log files themselves, and we really want those as forensic analysts, so that way when we're, looking over our data, doing a timeline analysis of events, or even if we're just troubleshooting applications, like what child process PID caused an error to happen, because maybe there's some other application that you can, use with this, if it's GDB or something else, you can use this data to help you gain further analysis. Typically, I use Strace when I'm going through something like with Ghidra or a different disassembler, and it's super powerful from both a dynamic analysis standpoint to help with your static analysis. So with all that being said, let's go ahead and rerun these commands, but this time we're going to create a new file per child process and then log all that data to disk. So just like before, we're going to go ahead and do -o, and we're going to call this example2 output.log. And instead of 1f, we're going to go ahead and do 2fs. And now with this, if I go ahead and do a listing in this current directory, we see we have example2 output.log, and then the child process ID is appended to that log file. And then with all of this, you have a unique process, or excuse me, you have a unique log per process. So again, in this example, we're just kind of looping through and printing some words from our secret 123 password. However, in a realistic application, being able to follow that parent-child relationship and understanding what syscalls they're getting made, that's going to be super key into an investigation you're doing, or even just kind of finding root cause analysis of at what point, do the wheels come off and things get a little crazy. So with that, I hope that you can take this lesson along with the previous lesson of learning how to inject and change return values of some syscalls and kind of start seeing a bigger picture of following child processes to see where you might need to inject certain syscalls at a specific level, which would then change when you call the particular parameter for injecting the given syscall, or even just the ability to gather a bunch of this data and then start digging a little bit deeper. Okay, so now we're going to go ahead and focus on more of a malware analysis side of the house, where we have an application and it's making outbound connections, and we want to see who it's talking to, what ports it's communicating on, and then also the data, if any, are being sent. So this is going to be a pretty heavy filtering and narrowing down on specific syscalls that we're interested in section. And the way that we can do that is via the -e flag, as we see in the slide here, followed by the syscall of interest. So often you're not going to know what that syscall of interest may be unless you have some insight into what this binary is. So maybe you run across something and you don't know that it's malware. And then you start diving a little deeper, like, oh, okay, we're making outbound connections. We got to figure out what this is. Or there's data getting sent out. How can we go ahead and inspect it a little more to have a better insight into what it's doing? And you can do that via the strace -e and then the syscall of interest. So whether that's read, write, connect, send, etc., you can go ahead and focus on only the data that you want. So we're going to, again, just try to make this as hands-on as possible. I'm going to jump into another demo here. And again, all of this is going to be able to get recreated in the GitHub lab exercise piece. The one piece here too that we're going to focus on is, this is great. We see the malware making outbound connections and we see it sending data, but how can we go ahead and pull more information out of that to have a little bit more actionable intelligence of what's going on, so that way we can take further steps to try to figure out what's being sent. Is it another payload? Are we just being used as like a host for further propagation of like a botnet, or what exactly is going on here? So that's going to kind of be the focus of the next section here. So for this next example, we're going to go ahead and try to focus in a little bit more on syscalls of interest to us and see how we can pull out a little bit more information from the underlying function calls that are occurring. So with that being said, we're going to go ahead and just jump right into example 3. And I'm just going to run it. And we see that my terminal kind of hangs a little bit here. Wait and see what's going on. I'm not seeing any messages to standard out. I'm going to go ahead and just Control-C this, and then rerun this example with strace at the front. Let's go ahead and see what syscalls are being made. All right, so looking at the bottom here, we've got some socket action, so that leads us to think network connections, and sure enough, we see a connect, and then we see a write syscall, and then we see a sleep. So it looks like we keep trying to connect to, in this case, our localhost, and we're just trying to send what appears to be a ELF file if we go ahead and look at the header here. So immediately we're seeing a handful of connects based on what we saw from our last example of the possibility of a bunch of forks and stuff going on. Let's go ahead and just filter in specifically for right now on just the connect syscalls. And we're also just going to go ahead and follow, and we're going to do just the connect syscall. So if we just do a -e connect, then that says, hey, let's just go ahead and look at these specific syscalls. We're going to run this again, just making sure that there's nothing flying by the screen that is something that I'm not seeing. Okay, and we have the -f to try to follow if there's any child processes. Cool. So looks like in this case there's no child processes. We're just dealing with the main parent process, and we just keep trying to connect to localhost on port 8000. That other thing that we saw earlier was that write syscall, and I mentioned that, hey, this looks like an elf header, mainly because it has the word elf in it, right? So let's go ahead and filter in on both connect and then the write syscall for what's going on here. So if you have multiple syscalls that you want to filter on, you can go ahead and just chain those together with a comma. And as we see here, we try to connect and then immediately send a stream of bytes over the wire. Interesting. And then if we look to the right here, we can see that this is how many bytes we're trying to send, and we're using the FD3. Doesn't really matter for this context, but just kind of going back to the looking at the man pages to understand, oh, these are the parameters, okay, this is what's going on here, and then our payload obviously being the ELF file. Neat. But with all that being said, we need to see more than just what that's showing us there for the actual strace. So strace by default will limit the characters. I think it's like 64 characters, might be a little bit less than that in terms of string size, except for full paths. They make it very clear that in the man page that full paths will always be shown. So let's go ahead and try to increase our string size a little bit. And we're going to just take out that connect right now. We only care about the write. And I want the string size to be, let's say, like 1,000. And okay, we see more data. We see that we have a fake cryptocurrency miner, but also these are bytes, right? If this is an ELF file getting transferred, this is bytes. These aren't strings. So seeing a bunch of zeros and hexadecimal characters getting printed to string, we're having some issues rendering them, and then also this doesn't really provide us with anything to take us to our next step of analysis. Fortunately, we can go ahead and actually have a whole ASCII dump get printed of particular file descriptors. So where we were a second ago, where we saw that we are curious of file descriptor 3 for write and the payload getting dumped, we can go ahead and filter in on just that and actually have a hex dump get printed of the whole file. So I'm going to go ahead and we're going to, again, remove both the follow and then also the connect. We're going to focus just on the write. And this time we're going to go ahead and do an equals 3, and that 3 is indicated, or that 3 links back to the file descriptor you're getting used here of 3. So I'm going to go ahead and clear my screen, and then we'll go ahead and run this, and then I'm going to kill the process. And sure enough, as I scroll up here in my tmux pane, we just got a hex dump of the binary being transferred across the wire. So that's really cool, because at this point, with a little bit of automation, we could take this hex dump and then actually recreate the ELF and then spend a little bit of time analyzing that. And here in this case, fake cryptocurrency miner, it just it has like a while true loop. It's nothing harmful to your machine. You're safe to run it if you do carve this all out. But the really nice thing about this too is that it looks like our third example has an embedded ELF binary. So in a scenario where you have an encoded, encrypted, etc., any kind of additional obfuscation or anything that's going to make your life harder when you're doing that static analysis and you're trying to rip those binaries out, it's just more of a time sink from the static analysis standpoint. So if there are ways that these binaries are getting written to disk or sent over the wire, and you can identify the file descriptor getting used, you can actually just go ahead and get a hex dump of it to disk. Now you still do have to do the legwork of taking that data and then recreating it into something a little bit more usable. However, this is a huge step forward in your analysis, regardless of what that may be. So with that being said, one of the, spoiler if you haven't seen the GitHub repo yet, one of the exercises for the end user is to actually take this and then recreate the embedded ELF binary and get it to run as part of the Packet Hacking Village kind of hands-on workshop piece for this talk. So that's something that you get to look forward to at the end of this talk. One key point that I haven't touched on yet is anti-debugging techniques that you may find in Linux or Unix malware out there to actually detect if they're being traced or not. So those coming from the Windows world that might be familiar with some anti-debugging techniques of the good old 132 API call of is debugger present, a very similar type of check can be done to see if the current program is being traced by the underlying ptrace library. The ptrace library is used by strace to actually do all of the inspection of the syscalls. So effectively, the binary does a pretty simple check to see, hey, is this program currently being inspected by ptrace? If so, exit or take different code path than normally would. Otherwise, continue. That's a pretty blatant example. There's definitely more creative examples that you can find online of anti-debugging techniques that go well beyond this talk, but this is something that I wanted to bring up in case you run across this in some exercises coming up. So now we've reached the end of the journey, and thank you very much for watching up until this point. Some key takeaways, just to do a quick recap, is that strace can provide super deep insight into what an application is doing, and from there you can actually influence the code path via return value injection or a different syscall injection. Additionally, if you're interested in seeing what's being read or written or sent to and from a host or to a file, you can also get an actual hex dump of the data being made if you know the file descriptor that is being used for said syscalls. And you can obtain those by filtering down on the specific syscalls of interest, whether that be a connection or a write, as we've gone through and demonstrated here. I hope that this quick little series on useful ways to leverage strace for Linux binary analysis has been useful to you, and I hope the examples kind of help fill any gaps or give you some hands-on experience to then go forth and use in your day-to-day.